Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can begin to loosen their grip, and where curiosity is allowed to speak softly. If you're settling into bed, resting on a couch, or simply trying to let the day fade into something more distant, you are in exactly the right place. Tonight, we're going to explore one of the most controversial and quietly unsettling ideas in all of biology. An idea that reshapes how we think about life, behaviour, and even ourselves. It asks a deceptively simple question. When nature chooses who survives, what exactly is it choosing for? Before we begin, if you enjoy these slow journeys through science, and if they help you rest, reflect, or simply feel less hurried, you are always welcome to like this video, subscribe, or leave a comment sharing where in the world you're listening from and what time it is for you right now. It is always a small comfort to know how widely scattered these quiet moments really are. Now feel free to dim the lights, let your shoulders relax and allow your breathing to slow. Nothing here will rush you. If your mind wanders, that is perfectly fine. We will still be here, gently unfolding the story. Tonight's journey begins with a strange little question, one that seems trivial at first but quietly opens a much larger door. Why does poop smell bad? It is not the sort of question that usually appears in textbooks, and certainly not one people expect to hear at the start of a biology lesson. And yet it turns out to be a surprisingly good place to begin. Because the answer is not about embarrassment, or social norms or bad manners. It is about survival, long before anyone was around to feel awkward about it. That smell is not accidental. It is not random. It is a message. To flies and bacteria, waste can be an opportunity. It is rich in nutrients, full of energy, a place where life can multiply quickly. To humans, however, that same place is dangerous. It can carry pathogens, parasites, and invisible threats that once caused enormous amounts of illness and death. Long before medicine, long before clean water systems, getting too close often meant getting sick. So over deep time, something quiet happened. Humans who felt drawn to that smell were more likely to touch, ingest, or linger near things that could harm them. Humans who felt a strong sense of disgust tended to step back, wrinkle their noses and move away. Those people were more likely to stay healthy long enough to have children, and their children inherited not the memory of the danger, but the instinct to avoid it. The smell became a warning sign, not because anyone planned it that way, but because those who ignored it tended not to leave much behind. This is the kind of story we are comfortable with. It fits our intuition. A trait helps an individual survive. The individual survives. The trait continues. Simple, clean, and reassuring. We often summarize this idea with a familiar phrase, survival of the fittest. In everyday language, that phrase sounds like strength, speed, intelligence, or dominance. We picture the fastest runner, the strongest fighter, the cleverest problem solver. We imagine nature as a competition that rewards the best individuals one by one. And for many situations, that picture seems to work well enough. But as soon as we look a little closer, cracks begin to appear, because nature is full of behaviours that do not look like self-interest at all. Honeybees will sting intruders to protect their hive, even though the act kills them. Worker ants spend their entire lives gathering food and building tunnels, never reproducing, never passing on anything of their own. Ground squirrels give loud alarm calls when predators approach, drawing attention to themselves and increasing their own risk, all to warn others nearby. If natural selection only rewards individuals who protect themselves, why would these behaviours exist at all? At first glance, they seem like mistakes, acts of generosity that should be weeded out over time. After all, an animal that sacrifices itself leaves fewer descendants. An individual that risks its life for others should, in theory, disappear from the population, and yet these behaviours are everywhere, not just in insects, but in birds, mammals, and even humans. Parents who give up sleep, safety, and comfort for their children, siblings who protect one another, communities that share food during hard times. Again and again, life seems willing to trade individual advantage for something else. So either nature is not as ruthless as we imagine, or our understanding of what it is selecting for is incomplete. This is the moment where many people reach for comforting explanations. Perhaps animals do these things for the good of the species. Perhaps nature cares about balance, harmony, or cooperation at the group level. These ideas feel intuitively satisfying, almost moral in tone. But biology is rarely that sentimental. Before we decide what natural selection favours, we need to step back and ask a quieter, more careful question. Not what looks noble or useful or fair, but what actually persists over time. What continues, not because it deserves to, but because it manages to stay in the game a little longer than the alternatives. The smell of waste did not evolve because it is polite. The alarm call did not evolve because it is brave. These traits remain because somehow, somewhere in the chain of copying that connects generations, they help something endure. And that raises the deeper question we will spend the rest of our journey exploring. When evolution chooses, what is it really choosing for? Not strength, not goodness, not even individuals, at least not always. Something smaller, quieter, more patient. And once you begin to see it, it changes the way everything else looks. When most people first learn about evolution, they're given a story that feels tidy and reassuring. Nature, we're told, is a kind of long-running competition. Individuals struggle. Some do better than others. The ones who are stronger, faster, smarter, or better adapted survive long enough to reproduce. Over time, those traits spread. The rest quietly disappear. This story is not entirely wrong, but it is incomplete in a way that matters. The phrase that carries it all is a familiar one: survival of the fittest. It sounds scientific, but it also sounds like common sense. In everyday language, being fit suggests being powerful, resilient, or impressive. We imagine animals locked in contests, winners passing on their strength, losers fading from the picture. It feels almost cinematic, and because it feels intuitive, we rarely stop to question it. Part of the reason this story sticks is that it matches how we experience the world. We see athletes train their bodies, students sharpen their minds, companies compete for dominance. We are surrounded by examples where individual effort seems to lead directly to individual success. It is natural to project that logic backward onto biology. Early interpretations of evolution leaned heavily on this way of thinking. Organisms were treated as the primary players. Each one was a contestant in a vast, slow-moving tournament. The environment was the referee. Natural selection simply rewarded those who played the game well. But this picture quietly assumes something that is not always true. It assumes that what benefits an individual in the short term will always be what persists in the long term. It assumes that nature keeps score the way we do, by watching bodies and behaviours and choosing winners accordingly. Yet evolution does not watch. It does not judge. It does not keep a list of champions. All it does is allow some things to continue while others stop. This difference may sound subtle, but it changes everything. Imagine a world where two animals behave very differently. One is cautious, avoids danger, and survives many years. The other is reckless, takes risks, and often dies young. If the cautious animal consistently leaves more offspring, the story seems straightforward. Caution spreads, recklessness fades. But now imagine that the reckless animal before dying young leaves many offspring very quickly. Perhaps its risky behaviour gives it access to resources or opportunities that cautious individuals never encounter. In that case, even though it lives a shorter life, it may leave behind more copies of whatever instructions shape that behaviour. From nature's perspective, the shorter life does not matter. There is no memory of the individual. There is only the continuation of patterns. This is where the comfortable myth begins to wobble. Fitness in biology does not mean strength or intelligence or even survival in the usual sense. It means something much quieter. It means leaving behind traces that do not vanish immediately. It means being part of a pattern that keeps repeating, even as individual bodies come and go. An organism can live a long, careful life and still contribute very little to the future. Another can live briefly and recklessly and leave a surprisingly large mark. Evolution does not favour virtue or wisdom. It favours continuation. Once you start thinking this way, some familiar ideas feel less solid. Take competition, for example. We often imagine evolution as a constant battle between individuals, each trying to outdo the other. But many traits that persist do not look competitive at all. They look cooperative. They look wasteful. They even look self-destructive. Why would nature allow behaviours that seem to undermine individual success? The simple story struggles here. It tries to explain cooperation as a side effect or a mistake, or something that only works when individuals somehow benefit directly. Sometimes that explanation fits. Often it does not. This is not because cooperation is rare. It is because the unit we are focusing on may be misplaced. By concentrating only on individuals, we are watching the wrong level of the process. We are looking at the stage, not the script. The actors come and go, but something else remains remarkably persistent beneath the performance. Another reason the individual-centered story feels so appealing is that it aligns neatly with how we think about responsibility and identity. We like to believe that outcomes reflect effort, that success belongs to those who earn it, and that failure is a natural filter removing what does not work. Biology, however, is indifferent to these ideas. It does not care about fairness or intention. It does not care how hard something tried. It only responds to what continues, and sometimes what continues is not what we expect. This is why phrases like "the strongest survive" are misleading. Strength on its own guarantees nothing. Neither does intelligence, creativity, or even adaptability, at least not in the way we usually mean it. Traits persist only if they manage to keep reappearing, generation after generation, despite accidents, changes, and losses along the way. At this point, it may feel as though the ground is shifting slightly beneath the story you thought you knew. That is a good sign. It means we're getting closer to how evolution actually works, not as a moral tale or a competitive drama, but as a slow filtering process that operates without awareness or intention. The familiar image of individuals fighting for survival is not useless. It is simply not deep enough to explain everything we see. To understand why certain behaviours endure, especially those that seem to contradict self-interest, we need to look beneath the surface of bodies and lifetimes. We need to follow what is being copied. Once we do that, the picture becomes stranger, but also clearer. The focus begins to shift away from individuals as the primary heroes of the story. Something smaller, more abstract, and far more patient starts to come into view. And with that shift, the story of evolution becomes less about winners and losers, and more about what quietly manages to stay. Once you begin to loosen your grip on the idea that evolution always rewards the most self-protective individual, certain scenes in nature start to feel quietly unsettling. Take the honeybee. When a hive is threatened, worker bees will rush toward the danger. Some will sting the intruder, tearing their own bodies in the process. The act is fatal. The bee does not survive the encounter. There is no chance to recover, no opportunity to reproduce afterward, no personal reward waiting at the end of the sacrifice. From the perspective of the individual bee, this behaviour makes no sense at all. Or consider the worker ant. She spends her entire life digging tunnels, carrying food, tending larvae, repairing the nest. She never lays eggs. She never passes on anything of her own. Her days are filled with labour, and then she dies. If evolution is a contest between individuals trying to secure their own future, this looks like a losing strategy taken to an extreme. And yet, ants are among the most successful organisms on Earth. These examples are not rare exceptions. They're everywhere once you start looking. Ground squirrels emit sharp alarm calls when predators approach. The sound alerts nearby squirrels, but it also draws attention to the caller, increasing its own risk. Wolves share food with injured pack members. Monkeys adopt orphaned infants. Birds take turns standing watch while others feed or rest. Again and again, individuals appear to place themselves in danger or inconvenience for the benefit of others. If natural selection simply filters out behaviours that reduce individual survival, these patterns should have disappeared long ago. Instead, they persist with remarkable consistency across species and environments. This is the point where the simple story of evolution begins to strain. One response is to soften the claim. Perhaps these behaviours are not truly altruistic. Perhaps the individual gains something subtle in return, such as future favours or social standing. Sometimes this is true. Cooperation can be a form of long-term self-interest, a delayed exchange that pays off later. But many cases resist this explanation. A bee that dies defending its hive will not benefit from future cooperation. An ant that never reproduces cannot trade effort for descendants. A squirrel calling out to warn relatives does not receive a guarantee of safety in return, so the question remains, why would evolution allow such behaviours to survive? At this stage, many people instinctively reach for a comforting idea. Maybe nature cares about groups. Maybe behaviours that help the group survive are favoured, even if they harm individuals. The species prospers, and so the behaviour continues. This explanation feels right, almost noble. It aligns with our moral instincts. We like to think that cooperation is rewarded at a higher level, that nature recognises the value of selflessness. But there is a problem hiding beneath the surface. Natural selection is not a judge watching from above, awarding points to species that behave well. It does not have a category labelled group success that it consults when making decisions. Selection works through copying and loss, through repetition and disappearance. For a trait to persist, whatever carries it must be copied more often than alternatives. Groups, unlike genes or individuals, do not copy themselves cleanly. There is no simple mechanism by which one entire group produces multiple, competing versions of itself, generation after generation, in the same way that smaller units do. Groups form, dissolve, merge, split, and change in messy ways. Their boundaries blur, their histories overlap. This makes them awkward candidates for being the primary targets of selection. That does not mean group-level effects never matter. It means they are difficult to place at the foundation of the process. If we rely on them too heavily, we end up with explanations that feel satisfying, but lack mechanical clarity. So we are left in an uncomfortable place. Individual-centered explanations fall short. Group-centered explanations feel vague. And the behaviours themselves refuse to go away. This discomfort is important. It signals that our current lens is inadequate. We're trying to explain a pattern using the wrong level of focus. To move forward, we need to pause and ask a different kind of question. Not who benefits, but what persists. Not who wins, but what keeps being copied. The bee that dies does not matter to evolution as an individual story. The ant that never reproduces does not register as a tragedy. These lives are brief notes in a much longer composition. What matters is whether the instructions that shape those behaviours continue to appear in future generations, carried quietly by others. This is a subtle shift, but once it happens, the puzzle begins to rearrange itself. Altruism may not be a contradiction after all. It may simply be pointing us towards something we've been overlooking, a quieter layer of the process, one that does not line up neatly with our everyday ideas of self and sacrifice. At this point in the journey, we're not ready to name that layer yet. Doing so too quickly would feel like a trick, a premature answer offered before the question has fully settled in. Instead, it is enough to notice the pattern and let it linger. Nature is full of acts that look generous, wasteful, or even suicidal when viewed at the level of individuals. And yet these acts remain, stubbornly and consistently across time and across species. Something is being preserved here, and whatever it is, it does not seem to care very much about individual lives. When the puzzle of altruism becomes too uncomfortable, there is a very natural place the mind wants to rest. Perhaps animals help one another because it benefits the group. Perhaps evolution favours behaviours that allow whole communities to survive, even if some individuals are lost along the way. Perhaps nature, in its own quiet way, rewards cooperation and balance. This idea feels soothing. It mirrors the way we like to think about ourselves. We admire people who sacrifice for their families, their communities, their nations. We tell stories where the group endures because individuals step aside. When we see bees defending a hive or ants building vast underground cities, it is tempting to imagine evolution nodding approvingly at their teamwork. For a long time, this way of thinking was common. Species were treated almost like characters with goals. They adapted in order to survive. They developed helpful traits for the good of the whole. Altruism, under this view, was not a mystery at all. It was simply what successful species did. And for a moment, everything seems to click back into place. But biology has a way of unsettling comfortable stories. The difficulty is not that cooperation never matters. It clearly does. Groups that work well together can outperform groups that do not. Colonies with better coordination can gather more food. Packs with stronger bonds can hunt more effectively. Communities that share resources may weather harsh conditions more easily. The problem lies deeper in the mechanics of how natural selection actually operates. Selection does not act on abstract ideas like the group or the species, unless those things can be copied, compared, and filtered in a very specific way. For selection to work at any level, there must be multiple versions of something competing at the same time. Some versions must persist longer or reproduce more often than others. And the differences must be passed along. Genes do this effortlessly. They are copied again and again. Some copies survive, some do not. Small differences accumulate. Individuals do this as well, though less cleanly. They are born, they live, they reproduce, or they fail to. Over many generations, patterns emerge. Groups, however, are messy. They do not reproduce in neat lines. A group does not usually split into two identical daughter groups that then compete side by side. Groups merge, fracture, absorb newcomers, lose members, and change their character constantly. Their boundaries blur, their histories overlap. It becomes very difficult to say where one group ends and another begins. Because of this, it is hard for selection to see groups as stable units in the same way it sees smaller things. This does not mean group-level effects never influence outcomes. It means they are rarely the foundation of the process. When we try to place them there, we end up with explanations that sound satisfying, but lack a clear mechanism. Imagine trying to explain the spread of a rumour by saying that neighbourhoods compete, without ever mentioning the people who actually speak, listen, and repeat the words. The neighbourhood matters, but the copying happens at a smaller scale. The same is true here. When we say that a species survives because it is cooperative, we are skipping over the question of how cooperative tendencies are copied and maintained in the first place. We are describing a pattern, not explaining its cause. This is why many biologists grew uneasy with pure group selection explanations. They seem to solve the emotional puzzle while leaving the mechanical one untouched. And yet, abandoning the group idea entirely feels wrong as well. After all, cooperation clearly exists. Social behaviour clearly matters. Entire ecosystems depend on interactions between organisms. So where does that leave us? In a strange middle ground. Group-level thinking captures something real about how life behaves, but it struggles to explain how those behaviours get built, maintained, and passed along through time. Individual-level thinking captures some of that process, but fails to account for widespread self-sacrifice. The tension between these views is not a failure of biology. It is a clue. It suggests that we are still looking at the right phenomenon through the wrong lens. We are describing what happens at one level, while the copying that drives it all happens at another. To move forward, we need to step away from asking who benefits, whether individual or group, and ask something simpler and more precise. What is being replicated often enough to matter? What form can survive repeated copying without dissolving into noise? Once that question is on the table, the comforting moral tone begins to fade. Nature does not preserve cooperation because it is kind. It preserves patterns that manage to keep reappearing, regardless of how they look to us. This realization can feel cold at first. It strips away the idea that evolution has preferences or values, but it also clears the ground for a deeper understanding, one that does not rely on vague notions of goodness or group purpose. We are not being asked to give up on cooperation. We are being asked to explain it properly. And to do that, we must go further back than individuals, further back than groups, to the basic conditions that make selection possible at all. Only then can the puzzle of altruism begin to make sense, not as an exception, but as a natural outcome of a much quieter process. The answer is not waiting at the level of colonies or communities. It is hidden in the logic of copying itself, patiently repeating beneath the surface, long before anyone noticed the pattern. To move forward, we need to do something that feels almost backwards. Instead of asking what natural selection favours, we need to ask what natural selection requires, not morally, not philosophically, mechanically. Natural selection is often spoken about as if it were an active force, something that reaches into the world and chooses. But it does nothing of the sort. It has no hands, no eyes, no intention. It is closer to a filter than a decision maker. Things pass through it, or they do not. And the filter itself is astonishingly simple. At its core, natural selection only needs a few conditions to be met. First, there must be copying. Something must be able to make another version of itself. The copy does not need to be perfect. It only needs to resemble the original closely enough to count as the same kind of thing. Second, there must be variation. Copies must sometimes differ, even slightly. If every copy were identical forever, nothing would change. The system would be frozen in place. Third, there must be limits: space, energy, time, attention. There must be fewer opportunities to continue than there are copies trying to persist. Without limits, everything would simply expand without consequence. And finally, there must be loss. Some copies must fail to continue. They fade out not because they are judged, but because there is no room for all of them to remain. That is it. No struggle is required, no improvement is guaranteed, no foresight is involved. When these conditions exist together, patterns begin to shift on their own. Some forms become more common, others quietly vanish. This is natural selection in its most stripped-down form. Notice what is missing. There is no mention of individuals or groups or even living things. Selection does not care what carries the pattern. It only cares that the pattern is copied, altered, constrained, and sometimes lost. This is why focusing too quickly on organisms can be misleading. Organisms are one way that copying happens, but they are not the only way. They are vehicles, not the engine. Once this becomes clear, a powerful question emerges. If natural selection works whenever these conditions are present, what kinds of things are best suited to pass through this filter successfully? The answer is not always what we expect. Imagine something extremely large trying to copy itself. The process is slow, errors are common, breaking the structure ruins the whole thing. Now imagine something extremely small. It copies easily, but any tiny disturbance destroys it completely. It has no room for meaningful variation. Between these extremes lies a sweet spot, something stable enough to persist, but flexible enough to change. Something small enough to copy efficiently, but complex enough to influence the world around it. Natural selection does not search for this balance, it stumbles into it. Over time, patterns that fall within this range simply tend to last longer. They pass through the filter more often, not because they're better in any moral sense, but because they are less likely to be erased by chance or competition. This perspective helps explain why earlier attempts to place individuals or groups at the center of evolution feel strained. Individuals are complex, fragile, and temporary. Groups are even more unstable. They change shape constantly. Their boundaries dissolve, their histories overlap. Neither offers the clean, repeatable structure that selection thrives on. Something else does. To see it, we have to let go of the idea that selection is about improvement. It is not a ladder climbing toward perfection. It is more like a tide washing over a beach. Shapes that crumble easily disappear. Shapes that hold together remain visible a little longer. Eventually the shoreline changes. This is also why natural selection does not guarantee sensible outcomes. It does not aim for efficiency, elegance, or fairness. It only reflects what manages to keep showing up. Once we frame selection this way, the earlier puzzles begin to feel less mysterious. Altruism no longer needs to be an exception carved out for noble reasons. It becomes a pattern that persists because the underlying instructions that produce it meet the conditions for continuation. The question is no longer why an individual would sacrifice itself. The question becomes whether the pattern that leads to sacrifice continues to be copied elsewhere. And that question has a very different answer. At this point, we are standing at the edge of a deeper shift. We have stepped away from stories about heroes and groups and intentions. We are looking instead at a process that is almost boring in its simplicity, yet immense in its consequences. Natural selection does not care about lives, it cares about repetition. And whatever is best at being repeated within the limits of the world it inhabits will quietly shape everything that follows. We are now ready to travel further back, to a time before animals, before plants, before anything we would recognize as alive. Because to understand why certain patterns persist today, we need to see how copying itself first took hold, long before bodies existed to carry it. To understand how copying came to dominate the story of life, we need to travel far back, beyond animals and plants, beyond cells and genes, to a time when the Earth was not yet alive in any meaningful sense. This was a world without memory. The early Earth was restless and loud. Heat surged from below, Lightning fractured the sky. Ultraviolet light poured down without restraint. Oceans boiled in places and froze in others. Simple molecules formed, broke apart, reformed, and drifted endlessly through air and water. Nothing here wanted to survive. Nothing planned to persist. Chemistry simply followed the rules it was given. Atoms collided. Bonds formed. Structures appeared briefly, then dissolved again. Most arrangements were unstable, falling apart almost as soon as they came together. But occasionally, by chance alone, something slightly different happened. A structure formed that didn't collapse immediately. It lingered. Not because it was good, not because it was useful, simply because, under those conditions, it held together a little longer than the alternatives. This small difference mattered more than it seemed. In a world defined by constant breakdown, persistence becomes a kind of quiet success. A structure that lasts longer has more time to interact with its surroundings. It has more chances to encounter energy, to bump into other molecules, to participate in further reactions. Over vast stretches of time, this simple fact begins to tilt the landscape. Most structures appear and vanish without consequence. A few remain just long enough to leave a faint trace. And among these rare survivors, an even rarer event can occur. One structure helps bring about the formation of another structure like itself. This is the moment where everything changes. The first replicator did not announce itself. It did not know what it was doing. It did not understand the significance of copying. It simply existed in a way that made repetition possible. Perhaps it acted as a template. Perhaps it catalyzed its own formation. The details remain uncertain, and scientists still debate exactly how this happened. But the logic does not depend on the specifics. The crucial point is simple. Once copying appears, even imperfect copying, the world is no longer the same. From that moment on, the environment contains something new, not life as we usually imagine it, but a pattern capable of making echoes of itself. These early copies were crude, they broke easily. They differed slightly from one another. Some formed more quickly, some fell apart more slowly. Some interacted with their surroundings in ways that accidentally protected them. Others vanished almost immediately. There was no competition in the dramatic sense, no struggle, no race. But there was limitation. Space was finite. Energy was unevenly distributed. Not every structure could persist. And so, without intention, a quiet sorting began. Forms that tended to last a little longer became more common. Forms that fell apart quickly became rare, not because they were punished, but because they had fewer chances to be repeated. It is important to notice what did not happen here. There was no drive toward complexity. No preference for elegance, no march toward intelligence. The world was not trying to invent life. It was simply allowing some patterns to reappear more often than others. This is sometimes misunderstood as a law of improvement, but it is better thought of as a law of stability. Structures that resist disruption remain visible. Structures that do not disappear. This idea can feel almost trivial, and yet it underlies everything that follows. Stability does not mean perfection. It does not even mean usefulness in any broad sense. It only means not falling apart right away. Once copying exists, however briefly and clumsily, it creates the conditions for selection to begin operating. Copies that persist longer are present more often. Copies that form faster appear more frequently. Copies that interact favourably with their surroundings are less likely to vanish. Over time, these small differences accumulate. The first replicator did not need to be common. It did not need to be efficient. It did not need to be likely. It only needed to arise once. Given enough time, even an event with a tiny chance becomes almost inevitable. The early Earth had time in abundance. Millions of years passed with no audience, no purpose, no pressure to hurry. Once replication began, everything that came after was built on that foundation. Layers of complexity were added slowly. Structures that could protect the replicator began to matter. Barriers formed, compartments emerged, reactions became more coordinated. Eventually, chemistry began to resemble something we would recognize as biology. But at this stage of the story, there were still no organisms, no cells, no genes in the modern sense. Only patterns copying themselves imperfectly, drifting through a chaotic environment, persisting when they could, vanishing when they could not. This is an uncomfortable origin for life. There is no spark of purpose, no guiding hand. But it is also a deeply humbling one. Everything that followed, from the first cell to the most complex brain, rests on this quiet beginning. Life did not begin with ambition, it began with repetition, and once repetition exists, even without awareness or intention, the world is forever changed. Patterns that can remember themselves, however briefly, begin to shape the future simply by continuing to exist. From here, the path toward modern life does not require design. It requires only time, variation, and limits. The rest unfolds slowly, almost reluctantly, one fragile copy at a time. Once copying appears, even in its simplest and most fragile form, the world is no longer just a place where things happen and then disappear. It becomes a place where the past can influence the future. Before replication, every chemical event on early Earth was forgetful. Molecules formed, broke apart, and left no lasting trace. The same reactions could happen again and again, but each time they started from scratch. Nothing accumulated, nothing remembered. Replication changes that quietly but completely. A structure that can help create another version of itself introduces a kind of memory into the system. Not memory in the sense of awareness or intention, but memory in the sense that a particular arrangement of matter can reappear because it has appeared before. The present begins to echo the past. This echo does not need to be perfect. In fact, perfection would be a problem. If every copy were identical forever, the system would stagnate. It would repeat endlessly without exploring anything new. Imperfection, small and occasional, is what keeps the process alive. When early replicators copied themselves, errors crept in. Some changes made the structure less stable, causing it to fall apart more easily. Others had little effect at all, and very rarely a change made the structure slightly better at persisting, perhaps by folding more tightly, interacting differently with its surroundings, or resisting breakdown just a bit longer. These differences did not matter immediately. There was no sudden jump, no dramatic shift, but over long stretches of time, they mattered enormously. In an environment with limited space and energy, not every copy could remain. Some lasted, others vanished, and because the ones that lasted were present more often, they tended to be copied again more frequently. The world began to favour certain patterns, not because it preferred them, but because they happened to stick around. It is tempting to imagine this as a race, with replicators competing aggressively for dominance. But that image is misleading. There was no starting line, no finish, no awareness of rivals. The process was quieter than that, more like a fog slowly lifting from one shape while thickening around another. Replication does not require desire. It does not require strategy. It only requires that some structures make more of themselves than others under the same conditions. Over time, this creates a subtle direction. Not a goal, but a bias. Patterns that copy more effectively become more common. Patterns that fail to copy fade away. The environment does not reward effort or intention. it simply allows repetition. This is the point where many people instinctively imagine selection acting on whole structures, choosing winners and losers like a referee. But nothing like that is happening. Selection is not an extra force layered on top of chemistry. It is the natural consequence of copying in a limited world. Once this is understood, the leap from chemistry to biology becomes much smaller. Life does not suddenly appear fully formed. It slowly emerges as copying structures accumulate features that help them persist. Some develop protective shells, others cluster together, some interact with molecules that provide energy. Each small addition increases the chance that the pattern will continue, not forever, but a little longer. Replication also introduces a new kind of vulnerability. A structure that copies itself is now exposed to the possibility of being outnumbered by its own variations. A version that copies slightly faster or breaks down slightly less often can gradually replace others without ever confronting them directly. This replacement does not feel dramatic. There is no moment when one replicator defeats another. There is only a gradual shift in what becomes common and what becomes rare. The important thing to notice here is that selection does not need to know what it is selecting for. It does not evaluate stability, speed, or efficiency. It simply reflects them over time. This is why early replicators did not need to be good. They only needed to be good enough. A structure that lasts a little longer than its neighbours will be present more often. A structure that copies a little faster will make up a larger share of the population. These tiny advantages compound quietly. Given enough time, even a slight bias can reshape the entire landscape. This also helps explain why randomness never disappears from evolution. Copying introduces variation, but it does not eliminate chance. Which replicators happen to be present at the right moment, in the right place, with the right resources, still matters. Luck and persistence are woven together from the very beginning. Replication turns time into a creative force. Without it, nothing accumulates. With it, even the smallest differences can echo forward, shaping what comes next. By the time we reach the world of cells and organisms, this logic is deeply ingrained. Bodies, behaviours, and entire ecosystems are built on the quiet mathematics of copying and loss, played out over unimaginably long spans of time. But we're not there yet. At this stage of the journey, there are still no organisms, no individuals, no lives in the familiar sense. Only patterns that remember themselves imperfectly, drifting through a world that neither notices nor cares. And yet, in this simple process lies the seed of everything that will follow. Once copying matters, the future is no longer just a repetition of the present. It becomes a story shaped by what manages to endure. Once copying becomes part of the world, something else inevitably follows. Not conflict in the dramatic sense, but crowding. A replicator that can make copies of itself does not exist in isolation. It occupies space. It uses materials. It depends on energy flowing through its environment, and those things are never infinite. Even on the early Earth, with its vast oceans and restless chemistry, there were limits. Only so many molecules could fit in a given place. Only so much energy could be captured at a given moment. This is where the idea of competition quietly enters the story. Not competition as a struggle between rivals, but competition as a consequence of sharing a limited world. Imagine a shallow pool where simple replicating structures drift and form. At first, when replicators are rare, space is abundant. A new copy can appear without displacing anything else. Growth feels effortless, but as copies accumulate, the situation changes. There is no longer room for every structure to persist. Some remain, others break apart or fail to form. Nothing aggressive is happening here. No structure is pushing another aside. but the outcome is the same: not everything can continue. This is enough for selection to begin shaping the population. Some replicators copy themselves more quickly, some last a little longer before falling apart, some are more resistant to disturbances in their environment. These differences are small, almost invisible in the moment. But when resources are limited, even small differences matter. A replicator that persists just a bit longer is more likely to be present when the next copying opportunity arises. A replicator that forms slightly more efficiently will tend to appear more often. Over time, these subtle biases accumulate. The word competition often brings to mind images of conflict, but here it is more like a slow filtering process. Think of it as too many leaves trying to float on a narrow stream. Some catch on rocks, some sink, some drift onward. The stream does not choose, it simply flows. It is important to notice that nothing in this process requires awareness or intention. Replicators do not know they are competing. They are not trying to outperform one another. They are simply subject to the same constraints. This is why the idea of fitness can be misleading if taken too literally. Fitness is not a property an object possesses in isolation. It is a relationship between a pattern and its environment. A structure that persists well in one setting may fail completely in another. And because environments change, sometimes unpredictably, success is never permanent. This also means that evolution does not guarantee the best possible outcome. It does not explore all options and choose the optimal one. It settles, again and again, for what works well enough under current conditions. Sometimes, a pattern spreads, not because it is superior in any deep sense, but because it happens to be present when conditions align in its favour. A sudden shift in temperature, a change in available materials, a random fluctuation that tips the balance. This element of chance is not a flaw in the system, it is a built-in feature. From the very beginning, persistence has been shaped by both structure and luck. As replicators become more common, another effect emerges. Copies that change too much tend to fall apart. Copies that change too little risk stagnation. Somewhere between these extremes lies a range where variation is frequent enough to explore new possibilities, but not so frequent that stability is lost entirely. Again, no one selects this balance. It emerges because extremes tend not to last. At this stage, the world is still far from anything we would call life. But the basic logic that will later shape organisms, behaviours and ecosystems is already in place. Copying, variation, limits, loss. Together, these create a quiet competition, one that operates without battles or trophies. There are no winners in the usual sense, only patterns that remain visible a little longer than others. This perspective helps dissolve another common misunderstanding. Evolution is not a story of progress marching steadily forward. It is a story of persistence under constraint, of what manages to stay, not what deserves to. Some replicators may dominate briefly, only to disappear when conditions shift. Others may linger in obscurity, neither thriving nor vanishing until chance gives them an opening. History, at this level, is not written by champions. It is written by survivors of circumstance. As time passes, replicators that are better at protecting themselves, better at using available energy, and better at maintaining their structure become more common. Slowly, almost reluctantly, the stage is set for something new. Systems begin to emerge that surround replicators with layers of support, walls, compartments, boundaries. Not because the world wants life, but because patterns that carry their own shelter tend to last longer. And with that, the story begins to edge closer to the world of cells, bodies, and the familiar complexity of living things. But even there, beneath all the visible drama, the same quiet competition continues, patient and indifferent, shaping what remains. As copying patterns became more common, the world they inhabited began to change in a subtle but important way. Replicators were no longer isolated curiosities drifting through a chaotic environment. They increasingly found themselves surrounded by other replicators, all drawing from the same limited pool of space and energy. In this crowded setting, a simple truth emerged. A replicator that could protect itself, even slightly, tended to last longer. And lasting longer meant more opportunities to be copied. Protection did not appear all at once. It arrived in small, accidental steps. A replicator that happened to fold in a way that shielded its fragile parts from disruption survived a little longer. Another that stuck to a surface avoided being swept away. Another became surrounded by molecules that reduced damage from heat or radiation. None of these changes were planned. They were not solutions to a problem in the way we usually imagine solutions. They were side effects of variation, retained only because they made disappearance less likely. Over immense spans of time, these small advantages accumulated. Replicators became wrapped in increasingly complex layers of support. What began as chemistry started to resemble architecture. Compartments formed. Boundaries emerged that separated an inside from an outside. Reactions that happened randomly before became localized, repeating in familiar patterns. Energy flows were captured and guided rather than dissipated. Slowly, the replicator was no longer naked. This is where the idea of an organism begins to take shape, not as a sudden invention, but as a gradual thickening of scaffolding around something that already existed. The organism did not appear first, and then acquire a purpose. The purpose, if we can call it that, was always the same, to allow a pattern to continue. In this view, bodies are not the main characters of the story. They are temporary structures, assembled and discarded over and over again. They are built not to last forever, but to last long enough. This can feel unsettling at first. We're used to thinking of ourselves as central, as the point of the process. But from the perspective of deep time, organisms are more like vehicles. They carry something forward, and then they are replaced. The patterns they carry, however, can persist for astonishing lengths of time. At some point along this path, replicators took on a form we would recognize today. Long chains made from a small set of repeating chemical letters began to dominate. These chains could be copied with reasonable accuracy, yet still allowed occasional variation. They were stable enough to endure, flexible enough to explore. We now call these chains genes. Genes are not instructions in the way a recipe instructs a cook. They do not specify outcomes in detail. They influence tendencies, biases, and probabilities. They shape how an organism develops and behaves by nudging complex processes in certain directions. Importantly, genes are not alive on their own. Outside the context of a body, they are inert. It is the surrounding machinery, the cellular environment, the layers of protection and regulation that allow them to function. But that machinery exists because, in the past, genes that built better machinery tended to persist. This creates a kind of circular relationship. Genes build bodies. Bodies protect genes. Neither makes sense without the other. But when we ask which came first in evolutionary terms, the answer lies with the replicating pattern. This way of thinking leads to a striking reframing. Organisms are not the ultimate beneficiaries of evolution. They are the means by which something else continues. A bird builds a nest. A mammal nurtures its young. A human plans for the future. All of these behaviors feel purposeful, intentional, deeply meaningful from the inside. And at the level of experience they are. But at the level of evolution, these actions matter only insofar as they influence which patterns remain. This does not strip life of meaning. It simply places meaning at a different level than mechanism. Once organisms exist, selection can shape not only their structures, but also their behaviors. Movement allows access to resources, sensing allows avoidance of danger, learning allows flexibility, social interaction allows coordination. Each new layer adds complexity, but the underlying logic remains unchanged. Patterns that manage to build effective vehicles tend to appear again. Patterns that fail to do so fade away. It is tempting to imagine that evolution is striving toward increasingly advanced forms, climbing a ladder of progress. But the reality is quieter. Evolution explores what is possible and retains what happens to persist. Sometimes this leads to complexity. Sometimes it leads to simplicity. Often it leads to strange compromises. Some organisms invest heavily in protection. Others reproduce quickly and accept fragility. Some rely on cooperation. Others on solitude. There is no single best strategy, only strategies that work well enough under particular conditions. Seen this way, life is not a grand design, but a long series of temporary solutions. Each organism is an experiment that lasts for a while, then ends. The patterns it carries may continue, slightly altered, into the next experiment. As we move forward, this perspective will become increasingly important, because once we accept that organisms are vehicles rather than endpoints, the puzzling behaviours we noticed earlier begin to look different. Sacrifice, cooperation, and even self-destruction no longer stand out as anomalies. They become understandable features of a system where what matters most is not the survival of the body, but the persistence of the pattern it carries. By now, the story has carried us from a restless chemical world to organisms wrapped around copying patterns. And yet, one question still lingers softly in the background. If natural selection works by copying, variation, and limits, then what exactly is being copied most reliably today? Why not entire bodies? Why not single atoms? Why not something in between? The answer is not dramatic. It is not intentional. It is simply what happens to work. Imagine trying to copy something extremely small. A single chemical letter, for instance. It can be copied easily, but it has almost no visible effect on its own. Changing it does not reliably change how an organism grows, behaves, or survives. It is too tiny to leave a recognizable fingerprint on the world. Selection cannot really see it, because its influence dissolves into noise. Now imagine trying to copy something extremely large, an entire body or a complete set of instructions taken as one solid block. This too turns out to be unstable. Large instructions are heavy, they are slow to reproduce, and when reproduction does happen, they tend to be shuffled, broken and rearranged. Pages are torn from the book, chapters are mixed, whole sections are exchanged. The copy no longer resembles the original closely enough to be preserved as a single unit. Between these extremes lies a narrow and surprisingly comfortable middle ground. Genes occupy this space. They are long enough to influence real traits. A gene can affect how a protein folds, how a cell responds, how a body develops, how a behaviour leans. Its presence can tilt probabilities in ways that matter over time, but genes are also short enough to be copied with reasonable faithfulness. They can survive the chaos of reproduction without being completely torn apart. They pass from one generation to the next as recognizable patterns, even though they are often reshuffled alongside others. This balance is not something evolution aimed for. It is simply where the process settled. Natural selection does not search the space of possibilities and choose the best option. It filters whatever happens to be there. Patterns that are too small fail to leave a mark. Patterns that are too large fail to remain intact. Patterns of just the right size keep reappearing. Over long spans of time, these patterns come to dominate, not because they are superior in any grand sense, but because they are the ones that can be copied, altered, and retained under real-world conditions. This is why genes feel oddly well suited to the role they play. They are not perfect, they mutate, they misfire, they interact in complicated ways, but they are good enough at persistence. It is also why thinking of genes as tiny commanders issuing orders can be misleading. A gene does not contain a blueprint for an organism in the way an architect draws a building. It is closer to a suggestion, a bias, a small nudge applied repeatedly across generations. Genes work because they influence outcomes just enough to matter, while remaining stable enough to survive the process that carries them forward. This perspective also helps explain why recombination, the mixing and reshuffling of instructions during reproduction, does not destroy evolution. In fact, it depends on it. Large instructions would be hopelessly scrambled, tiny ones would be lost in the shuffle. Genes, sitting in the middle, are reshuffled but not erased. They behave like phrases rather than entire books. A phrase can move to a new paragraph and still make sense. A single letter cannot. Again, nothing chose this arrangement. There was no moment when nature decided that genes were the ideal size. It simply happened that patterns of this scale endured, while others faded. This realization strips away another layer of intention we often project onto biology. Evolution did not design genes because they are clever. Genes appear clever because they are the kind of thing that survives an unintelligent process. Seen this way, the gene-centered view is not a claim about importance or dominance, it is a claim about visibility. Genes are the scale at which selection can most clearly register cause and effect. Change a gene, and something often changes in the organism. Keep that gene, and its influence may echo forward. Lose it, and the echo fades. Bodies are too temporary, atoms are too silent, genes sit in between, whispering just loudly enough for time to hear them. This does not mean genes act alone. They do not. Their effects depend on context, on environment, on timing, on countless interactions. But as units of persistence, they strike a workable balance. And once this balance is in place, a powerful reinterpretation becomes possible. If genes are the most reliable carriers of influence across generations, then many of the behaviors we see in organisms may be better understood as ways of protecting, copying, or amplifying these patterns, rather than as strategies for individual survival. This idea will feel unsettling at first. It will seem to turn familiar stories upside down. Acts that look generous, foolish, or self-destructive at the level of individuals may look very different when viewed through the quieter lens of overlapping instructions. We're not there yet. For now, it is enough to see why genes occupy the role they do. Not because they were chosen, but because everything else gradually fell away. The process did not ask what was best. It simply kept what lasted, and what lasted, again and again, were patterns of just the right size to be remembered. Now that genes have taken their place as the most reliable units of persistence, an old puzzle returns, but in a different light. Why would an organism risk itself for another? At the level of individual experience, altruism feels simple and familiar. A warning call, a shared meal, a body placed between danger and someone else. These actions feel generous, sometimes heroic, sometimes instinctive. They feel meaningful because they involve loss, and because that loss is real. But earlier we saw how stubborn this pattern is. Across species and environments, individuals repeatedly do things that reduce their own chances of survival. And they do so without hesitation, without visible reward. When viewed through the lens of individual success, altruism looks like a mistake that should have been erased long ago. When viewed through the lens of genes, something quieter appears. Relatives are not identical copies of one another, but they overlap. They carry instructions that echo across family lines. A sibling shares much of what shaped you. A parent passes on fragments of themselves. Cousins, more distantly, still carry faint reflections of the same patterns. These overlaps matter. If a particular set of instructions influences behavior in a way that protects relatives, then those instructions may continue even if one carrier does not. The body is lost, but the pattern persists elsewhere. This is not a strategy anyone chooses. It is not a calculation performed in the moment. It is a tendency that emerges because instructions that produce such behavior tend to remain visible across generations. The ground squirrel's alarm call begins to look different here. The call draws attention to the caller, increasing its own risk, but it also alerts nearby relatives who share many of the same instructions. If those relatives survive, the echo of the pattern continues. The action feels selfless at the level of experience, and it is. This squirrel does not benefit personally, but the instructions that shape the behavior may. The same logic applies to food sharing among wolves, to adoption among primates, to countless small acts of cooperation woven through the natural world. Each case involves a local cost and a distributed benefit. This reframing can feel unsettling. It can sound as though kindness is being reduced to cold arithmetic, as though care is nothing more than a trick of inheritance. But this reaction comes from confusing explanation with experience. Genes do not feel generosity. They do not weigh outcomes. They do not understand sacrifice. They simply persist or vanish, depending on whether the patterns they produce tend to reappear. Altruism, under this view, is not an illusion. It is real behavior with real consequences. What changes is not the behavior itself, but our understanding of why it remains. This perspective also dissolves a common misconception. Altruism does not require that individuals be blind to self-interest. Many cooperative behaviors are flexible, context-dependent, and sensitive to social cues. They are not rigid commands. The important point is that instructions influencing such behaviors can persist, even when they occasionally lead to individual loss, so long as the overall pattern continues through others. This is why altruism is often strongest among close relatives, weaker among distant ones, and most fragile among strangers. The echoes fade with distance, the overlap thins, and yet, even among strangers, cooperation can arise. Shared histories, repeated interactions, and social structures can extend the reach of these patterns beyond simple family lines. But the core logic remains the same. Persistence does not require that every carrier survive. It only requires that enough do. This idea turns a familiar story upside down. Instead of individuals sacrificing themselves for the group, we see patterns surviving through networks of overlapping carriers. The group is not the target, the individual is not the goal, the continuity of the pattern is what quietly matters. There is a strange elegance in this, a kind of unintended harmony. Behaviours that feel generous from the inside can arise naturally from a process that has no concept of generosity at all. At the same time, the idea remains emotionally difficult. It resists our instinct to place agency and intention at the centre of explanation. It asks us to accept that some of the most meaningful acts in nature emerge from a process that does not recognise meaning. This discomfort is not a flaw. It is a sign that we are holding two truths at once. At the level of mechanisms, altruism can be understood as a pattern that persists because it echoes through related carriers. At the level of experience, altruism remains an act of care, risk, and connection. One does not erase the other. As we sit with this tension, another question quietly rises. If genes persist by overlapping and echoing, Why do organisms mix and reshuffle those instructions at all? Why not simply copy them intact, generation after generation, avoiding loss and dilution? Why does life insist on sharing, blending, and recombining what seems so carefully preserved? That mystery draws us gently onward, toward a process that looks inefficient, costly, and unnecessary at first glance, yet remains one of the most widespread features of life on Earth. Once genes are understood as the quiet carriers of influence, another long-standing puzzle comes into view. Why does life mix them? At first glance, sexual reproduction seems inefficient, even reckless. An organism invests time and energy to find a partner. It shares its instructions instead of copying them intact. From one generation to the next, only part of what it carries is passed on, while the rest is lost to reshuffling. If persistence is the goal, this looks like a strange choice. There's a simpler alternative. Some organisms reproduce by copying themselves almost entirely. No searching, no sharing, no blending. The instructions pass forward cleanly, generation after generation. From the narrow perspective of short-term continuation, this seems safer. And yet, across much of the living world, sex persists. Not everywhere, not always, but often enough to demand an explanation. The temptation is to frame this as a problem evolution solved once, long ago, with a clever trick. But that framing is misleading. Sexual reproduction is not a single invention with a single justification. It is a pattern that keeps reappearing because, under many conditions, it manages to endure. To see why, it helps to think less about efficiency and more about uncertainty. The world is not stable, environments change, conditions shift slowly at times, abruptly at others. A set of instructions that works well today may fail tomorrow, not because it is flawed, but because the world it depends on has moved on. Copying instructions intact preserves what worked in the past. Mixing instructions creates variation that may work in the future. This is not foresight, it is insurance. When instructions are reshuffled, new combinations appear. Some are worse than before, some are no different, and occasionally, one happens to fit a new set of conditions better than anything that came before. Sex spreads risk across generations. It avoids placing all bets on a single arrangement. This does not mean sexual reproduction is always better. In stable environments, copying without change can be remarkably effective. Many organisms thrive this way for long periods, but stability is fragile. When it breaks, uniformity becomes a liability. The world rewards flexibility, but only after it has changed. From the gene's perspective, mixing is a gamble that pays off often enough to persist. Genes that find themselves frequently reshuffled do not disappear simply because they are shared. They survive if they tend to end up in combinations that continue. Some instructions even benefit directly from mixing. When combined with different partners, their effects may become stronger, more adaptable, or more resilient. Over time, such instructions become associated with processes that promote reshuffling itself. This is not intention, it is association. Patterns that survive in a mixed system tend to be those that tolerate mixing well. Over many generations, this creates a population where sharing becomes normal, even expected. Another way to see this is through a simple image. Imagine playing a long game with a deck of cards. If you keep the same hand forever, it may serve you well for a while, but if the rules change, you are stuck. Shuffling the deck occasionally risks worse hands, but it also gives you a chance at better ones. Sex is that shuffle. It introduces noise into the system, but it is a kind of noise that explores possibilities. Not all noise is destructive. Some noise prevents stagnation. This also helps explain why sexual reproduction often coexists with mechanisms that limit how much change happens at once. Too much reshuffling would destroy useful patterns entirely. Too little would freeze them in place. Again, there is a balance not chosen but settled into. From the outside, sex can look wasteful. From the inside, it feels essential. But at the level of deep time, it is neither. It is simply one of the ways copying continues under uncertainty. Importantly, this view does not reduce sex to a cold calculation. It does not deny the richness of attraction, bonding, pleasure, or care. Those experiences are real and powerful at the level of organisms. What it does suggest is that beneath those experiences lies a process that does not share our perspective. A process that preserves mixing because on average mixing keeps patterns visible in a changing world. Sex persists not because it is optimal, but because it is robust. It survives not by guaranteeing success, but by tolerating failure. As we let this idea settle, another quiet realization follows. Even when patterns persist, even when reshuffling helps, outcomes are never fully determined by advantage alone. Sometimes, what remains is shaped less by how well something works, and more by what happens to be there when circumstances shift. This brings us to the role of chance, and to a side of evolution that feels less like selection, and more like history unfolding in the dark. Up to this point, the story of evolution may still feel guided, even if unintentionally. Patterns persist because they copy well. Instructions endure because they fit their environment. Behaviours spread because they echo through families. There is a sense, however gentle, that what remains is what works. But there is another force woven through this process, one that does not care what works at all. Chance. Not chance as a rare interruption, but chance as a constant companion. Imagine a small population, isolated by geography or circumstance. A handful of organisms live in a quiet pocket of the world. They carry a mix of instructions, some common, some rare. Now imagine that a storm passes through, or a drought, or a sudden cold spell. Not because of any trait, not because of any advantage or weakness, but simply because weather does what it does. Some individuals survive, others do not. The instructions they carry disappear or persist accordingly, not because they were better suited, but because their carriers happen to be in the right place at the right time. This is genetic drift. It is evolution by accident, not by advantage. In large populations, chance tends to average out. Individual losses are absorbed by sheer numbers, but in small populations, randomness can dominate. A few unlucky events can reshape the entire future. A trait that offers no benefit can become common simply because it was carried by those who happen to survive. A useful trait can vanish if its carriers are lost early. Over time, these random shifts accumulate, leaving a genetic signature that tells a story of history rather than optimization. This is why evolution cannot be understood as a steady march toward improvement. It is not always sculpted by what works best. Often, it is shaped by what was not removed. The image of coins tossed in the dark captures this well. Each toss is independent. There is no memory, no correction. Over many tosses, patterns emerge, but not because the coins are trying to favour one side. They simply fall as they fall. In the same way, genetic drift does not push life in a particular direction. It nudges it unpredictably, especially when numbers are small and outcomes are fragile. This realization can feel unsettling. It challenges the comforting idea that nature awards merit, that success reflects superiority, that persistence implies value. Instead, it suggests that much of what exists today may simply be the result of survival through noise. Traits that seem meaningful to us may be historical accidents. Features we admire may have persisted not because they were ideal, but because they were not costly enough to be removed and not unlucky enough to disappear. This does not mean selection disappears. It means selection shares the stage. Fitness still matters. Some patterns do persist because they fit their environment better. But fitness does not operate alone. It is constantly interrupted, amplified, or muted by chance. This is especially true during moments of transition, when populations shrink, when environments change rapidly, when small groups split off and form new lineages. At these moments, history can hinge on a handful of outcomes that no amount of adaptation could predict. Over long periods, drift can create differences between populations that have nothing to do with advantage. It can shape appearances, behaviours, and tendencies in ways that tell us more about past bottlenecks than about present needs. This is why evolution often looks messy, why similar environments host very different organisms, why traits appear that seem unnecessary or even slightly harmful, why there is no single solution to survival. Drift reminds us that evolution is not a design process. It is a record of what happened to remain. Understanding this does not weaken the gene-centered view, it completes it. It adds humility. It acknowledges that copying and persistence operate within a world that is unpredictable and uneven. Genes do not always spread because they are helpful. Sometimes they spread because they were carried through a narrow gate by chance. Sometimes they persist because nothing came along to remove them. This perspective also has a calming effect. It softens the pressure to see every trait as purposeful. It allows for looseness, for imperfection, for quirks that exist simply because they exist. Life is not optimized, it is accumulated. As we move forward, this realization prepares us for another shift. If chance plays such a large role, if traits persist without clear intent or precision, then the idea that genes act like exact instructions begins to wobble. Perhaps genes do not specify outcomes as cleanly as we imagine. Perhaps they do not draw blueprints so much as set tendencies, nudging systems that are already noisy and complex. To understand that, we need to look more closely at how genes relate to traits and why that relationship is far less precise than the language we often use to describe it. As the role of chance settles into the story, another quiet assumption begins to loosen its grip. We often speak about genes as if they were precise instructions, as if each one were responsible for a specific feature, a clear command that says, build this, or do that. Eye colour, height, temperament, talent. The language we use suggests neat lines of cause and effect. But this neatness is an illusion. Genes do not work in isolation. They do not act one at a time, and they do not dictate outcomes with certainty. What they do instead is influence tendencies within systems that are already complex, dynamic, and sensitive to context. A single gene can affect many traits. A single trait can be influenced by many genes. The same instruction can lead to different outcomes depending on when it's active, where it is active, and what else is happening at the same time. Imagine a room filled with dimmer switches rather than light switches. No switch simply turns something on or off. Each one adjusts intensity, timing, and interaction. Some switches matter only when others are set a certain way. Some matter early, shaping the structure of the room. Others matter later, fine-tuning what already exists. Genes behave much like this. They participate in networks. They influence processes rather than dictate results. They shape probabilities rather than outcomes. And they do so within environments that are constantly changing, both outside the organism and within it. This is why trying to trace a straight line from a gene to a trait so often leads to frustration. The line bends, it splits, it loops back on itself. It passes through layers of regulation, interaction, and feedback. Timing matters. The same instruction can have a very different effect early in development than it does later. Context matters. A gene that contributes to one outcome in one environment may contribute to a different outcome in another. Interaction matters. Instructions rarely act alone. They combine, amplify, dampen, and sometimes cancel one another. None of this is a flaw in biology. It is a feature. A system built on rigid blueprints would be fragile. Any small change would cause collapse. A system built on flexible tendencies can absorb variation, adjust to circumstances, and continue functioning even when parts are altered. This fuzziness allows life to persist in a world that refuses to stay still. It also helps explain why simple narratives about genetic destiny feel compelling but fall apart under scrutiny. It is tempting to believe that genes fix who we are, that they lock in our future from the moment we are formed. But this view overestimates precision and underestimates interaction. Genes bias outcomes. They do not guarantee them. This perspective also reframes how we think about responsibility and identity. If genes were strict commands, then individuals would be little more than executions of code. But because genes operate through layers of interaction, there is room for flexibility, learning, adaptation, and experience. Biology leaves space. Even at the cellular level, systems are responsive rather than mechanical. Signals are interpreted. Thresholds are crossed gradually. Feedback loops adjust behavior moment by moment. Noise is not eliminated, it is managed. At higher levels, this flexibility becomes even more pronounced. Development responds to environment. Brains change with experience. Behavior adapts to context. The same genetic background can support a wide range of outcomes depending on how life unfolds. This does not mean genes are unimportant. They matter deeply. They shape what is possible, they constrain and enable, but they do not script the story line by line. Understanding this helps correct another common misunderstanding. When we say that genes are the units of selection, we're not saying that genes control everything. We're saying that genes are the units through which influence tends to persist across generations. What happens within a lifetime is shaped by many forces. Genes are one of them, not the whole. This realization can feel like a relief. It softens the pressure to find a genetic explanation for every difference. It allows for complexity without confusion. It invites humility rather than certainty. Biology, at its core, is not precise because the world it operates in is not precise. It evolved in a landscape full of variation, unpredictability, and change. A fuzzy system is not a failure in such a world. It is an adaptation. As we let go of the illusion of precision, another language problem comes into focus. If genes do not plan, command, or decide, then the words we use to describe them can quietly mislead us, especially when we borrow terms from human psychology to describe molecular processes. This brings us to a single word that has caused more misunderstanding than almost any other in this conversation. A word that was meant as a metaphor but often lands as a judgment. By this point, the mechanics of the gene-centered view have settled into place. Patterns persist by being copied. Genes endure by influencing outcomes just enough to matter. Altruism, cooperation, and even sacrifice can arise without intention, guided by echoes rather than plans, and yet for many listeners something still feels off. That discomfort often traces back to a single word: selfish. It is a word that carries weight. In everyday life, it describes a failure of care, a narrowing of concern, a turning away from others. It implies intention, choice, and moral fault. When applied to people, it is rarely neutral. So when we hear genes described this way, something inside us reacts. It sounds as though biology is accusing life itself of moral coldness. It sounds as though kindness has been exposed as a lie. It sounds personal, even when it is not meant to be. This reaction is understandable, but it arises from a mismatch between metaphor and mechanism. Genes are not selfish in the way people can be selfish. They do not want. They do not decide. They do not weigh outcomes or pursue goals. They are molecules following physical rules, copied or not copied, present or absent. The word selfish was never meant to describe intention. It was meant to highlight a pattern in which instructions that tend to persist do so regardless of the fate of individual carriers. A pattern in which outcomes that feel generous or cruel at the level of experience can arise from a process that recognizes neither. As metaphors go, it is sharp and memorable, but sharp metaphors cut both ways. When we forget that selfish is shorthand, we begin to smuggle human emotions into places they do not belong. We imagine genes scheming, competing, manipulating bodies for their own ends. We picture life as a battlefield of intentions. This is not what the theory claims. The gene-centered view does not say that genes are selfish agents. It says that persistence behaves as if instructions that survive matter more than the vehicles that carry them. The as if is crucial. Remove it, and the meaning shifts dramatically. Language, especially in science, often borrows familiar words to describe unfamiliar processes. This makes ideas accessible, but it also invites misunderstanding. When the metaphor is taken literally, explanation becomes accusation. This is why the emotional response to the word selfish can be so strong. It feels like a moral statement masquerading as a scientific one, but the science itself is morally silent. It describes how patterns endure. It does not tell us how we should live. It does not evaluate kindness or cruelty. It does not assign praise or blame. The discomfort we feel is not a revelation about nature. It is a reminder about language. Consider how often we describe non-living systems using human terms. We say that rivers carve landscapes, that markets punish mistakes, that machines learn. None of these systems possess intention, yet the metaphors help us think. The danger comes when we forget that they are metaphors. Genes do not act out of greed. They do not exploit organisms. They do not prefer one outcome over another. They simply persist when the conditions allow them to persist. If a pattern produces care, that care is real. If a pattern produces harm, that harm is real. But the pattern itself does not feel either. Recognizing this helps untangle explanation from judgment. It allows us to appreciate the explanatory power of the gene-centered view without absorbing its metaphors as moral claims. This distinction matters deeply, especially when ideas move from biology into culture. Misunderstood metaphors can harden into worldviews. They can be used to justify indifference, competition, or despair, all under the banner of nature. But nature does not instruct us to behave in any particular way. It describes how things came to be. Understanding the mechanics of persistence does not tell us what we owe one another. It tells us how patterns endured long enough for us to be here asking the question. This is why the gene-centered view must be handled with care. It is powerful. It illuminates puzzles that once seemed contradictory. But when stripped of nuance, it can sound colder than it is. The solution is not to reject the idea. It is to hold it correctly. Genes are not villains. They are not heroes. They are not anything at all in the moral sense. They are simply part of a process that unfolds without regard for our categories. Once we let go of the word selfish as a description of intent, the tension eases. What remains is a framework for understanding persistence, not a verdict on meaning. And this brings us to an important boundary. Even the most accurate explanation of how something works is not the same as guidance on how to live. Confusing the two can lead us far from where science is meant to stop. By now, the gene-centered view has done its work. It has explained how patterns persist without intention. It has shown how cooperation can arise without kindness being planned. It has revealed how chance, context, and repetition shape the living world beneath everything we notice. And yet at this point, another kind of discomfort can quietly surface. If organisms are vehicles, if genes persist without caring, if much of what exists is shaped by accident as much as advantage, then what does that say about us? About choice, responsibility, love, or purpose? It is tempting at this stage to slide from explanation into philosophy, to take a description of how life came to be and treat it as a prescription for how life should be lived. This is where many misunderstandings begin. The gene-centered view explains patterns of persistence. It does not explain meaning. It describes mechanisms. It does not assign value. It tells us how copying works in a limited world. It does not tell us how to treat one another. When these boundaries blur, a true idea can become a bad life philosophy. Taken too literally, the idea that organisms are vehicles can feel diminishing. It can sound as though individuality is an illusion, as though care is a trick, as though choice is a side effect rather than something real. But this reaction comes from asking the theory to answer questions it was never designed to address. Science answers how. It does not answer why, in the human sense. The fact that a process lacks intention does not mean the experiences it produces lack meaning. A sunset is not designed, but it is still beautiful. A melody follows physical rules, but it still moves us. A thought arises from neural activity, but it still feels like a thought. Explanation does not erase experience. The gene-centered view operates at a scale far removed from daily life. It speaks in generations, not moments. It describes patterns across populations, not choices within a single mind. It is concerned with what remains, not with what it feels like to be here now. Trying to live according to it would be like trying to navigate a conversation using only grammar rules. You would know how sentences are structured, but you would miss what anyone is actually saying. At the level where we live, different rules matter. We experience ourselves as individuals. We feel care, curiosity, fear, and attachment. We make decisions. We reflect. We imagine futures and regret pasts. These experiences are not illusions simply because they emerge from deeper processes. They are real at the level where meaning exists. The mistake is not in understanding the mechanism. The mistake is in letting the mechanism swallow everything else. Evolution does not tell you what matters to you. It does not tell you who to love, what to protect, or how to act when faced with uncertainty. Those questions arise at a different level of description, one that science can inform but not replace. Holding both levels at once is not a contradiction. It is a skill. You can understand that your body is shaped by ancient copying processes and still experience yourself as a thinking, choosing being. You can recognize that cooperation evolved without intention and still choose to cooperate because it matters to you. The fact that kindness can be explained does not make it less kind. In a way, this realization is freeing. It allows science to do what it does best without burdening it with expectations it cannot meet. It allows us to appreciate the elegance of the mechanism without mistaking it for a moral compass. A true explanation becomes harmful only when it is stretched beyond its proper scope. The gene-centered view is powerful because it strips away comforting stories and replaces them with something quieter and more precise. But precision is not purpose. Mechanism is not meaning. Description is not direction. Once this boundary is respected, the tension dissolves. You're not required to see yourself as a disposable vehicle just because evolution can be described that way. That description exists at a scale where individuality blurs into pattern. At the scale where you live, individuality is everything. Science explains how the stage was built. It does not write the play. As we approach the end of this journey, the noise of explanation begins to settle. What remains is not a cold universe, nor a comforting one, but a world that produced beings capable of asking questions, feeling wonder, and reflecting on their own origins. Understanding how that happened does not take anything away from the experience of being here. If anything, it makes it quieter, deeper, and more astonishing. As we come to the end of this long and gentle exploration, it helps to let the ideas rest for a moment. The machinery of evolution is vast and impersonal, copying without intention, variation without foresight, persistence shaped by limits, chance, and time, genes echoing forward through countless bodies, most of which flicker briefly and vanish. That story can feel distant, even cold, when told all at once. But when the noise of explanation settles, something simpler remains. You are here, not as a pattern in the abstract, not as an instruction set drifting through generations, but as a living, experiencing being. You notice, you care, you wonder, you feel the weight of moments, the pull of relationships, the quiet importance of choices. None of that is erased by understanding how it came to be. In fact, the opposite is true. The gene-centered view does not say that life was designed for meaning. It says that meaning emerged anyway, from a process that did not aim, did not plan, did not care, arose creatures capable of caring deeply. From repetition arose reflection. From copying arose consciousness. This is not a contradiction, it is a layering. At one level, life is shaped by ancient processes that operate without awareness. At another level, life is lived moment by moment, rich with intention, emotion, and thought. These levels do not compete, they coexist. When you decide to help someone, that decision is real. When you feel love, that feeling matters. When you choose restraint, curiosity, or kindness, those choices shape your world. They do not need to be justified by evolutionary advantage to be meaningful. Understanding origins does not flatten experience. It deepens it. It reminds us that what feels ordinary is the outcome of an extraordinary history. That the ability to pause, to reflect, to ask questions like the ones we have explored here, rests on an unbroken chain of persistence stretching back billions of years. And yet, that chain does not dictate what you do with this moment. Evolution explains how the conditions for experience arose. It does not dictate how experience should be used. This distinction is easy to lose in a world that loves simple narratives. Either life has purpose, or it does not. Either we are shaped by biology, or we are free. But reality is rarely so tidy. We are shaped, and we choose. We are influenced, and we reflect. We inherit tendencies, and we respond to them. The mechanisms beneath us are not scripts. They are foundations. They make certain things possible, but they do not write the ending. In the quiet space where science ends, something else begins. Not an answer, but a stance. A way of holding knowledge without letting it harden into certainty or despair. The gene-centered view invites humility. It reminds us that we are not the center of the universe, not the goal of evolution, not the final form of anything. But it also invites gratitude. Against overwhelming odds, patterns persisted long enough for awareness to arise. Life is not designed, but it is still lived. And being lived is not a small thing. As you listen, perhaps in the dim light before sleep, it is enough to let these ideas drift without forcing them to resolve. You do not need to reconcile every level of explanation. You do not need to extract a lesson. You can simply notice that the same universe capable of blind repetition also gave rise to reflection, that the same process that does not care produced beings who do. That is not a moral conclusion, it is an observation, and sometimes observation is enough. So as this exploration comes to rest, you can let go of the machinery and return to the quiet fact of being here. Breathing, thinking, aware. The story of life did not promise meaning, but somehow meaning appeared. And tonight, in this small moment, that is what remains.